interacting particle system. And the question that I like to address in this talk is how introducing inhomogeneities to the model can affect relevant probabilities associated to the model. Now, this talk will be more on the mathematical side of things, but the whole field of interacting particle systems originates from physics. So I will talk a little about, introduce a little about this field. So interacting particle systems are continuous time Markov processes. They usually take place on graphs. So we have a set of sites S, which is usually infinite but countable, and we think about this set of sites as vertices of the graph. And we have E, which is the set of possible states, which is finite. And at each point in time, the state of this continuous time Markov process is given by assigning a value from E, the possible set of states, to each vertex of the graph. And I will denote configurations by Xi. A configuration assigns a state to every site in S. And in general, we talk about spin systems. This is the most well-studied interacting particle systems are the spin systems in which sites can be in state 0 or 1. And the transition dynamics, the evolution in time of this Markov process is determined by transition rates. These transition rates are local and simple functions of finite set of vertices. For each finite set A, CA determines the rate at which the sites in this finite set A will change their states. And under certain conditions, these local rules determine the evolution of the system in a unique way, and then we have a well-defined continuous time Markov process. And the interpretation of configuration and transition rates depends on which type of interacting particle system we are talking about. And this whole field was established in the late 1960s by the work of Dauphine and Spitzer, and it was originally motivated by statistical mechanics, and it soon turns out that this is also a natural generalization of classical models in probability theory. And let me mention some interacting particle systems. The first 4 models are considered to be the classical interacting particle systems models. The contact process, which can be seen as the model for the spread of epidemics, and this is the process that I will talk about in my talk. There's the exclusion process, which can be seen as a model of particle motion. The voter model, which models computing populations or competing populations or competing opinions. The stochasticizing model, which is the model, the mathematical model of ferromagnetism. So these 4 are the classical model of interacting particle systems. But of course, later on, more models were introduced. And one model that could be particularly interesting from a physicist point of view is kinetically constrained models. And these are the mathematical models for systems that undergo a liquid glass transition. So the model that I will be talking about in my talk is the contact process, which, as I said, is a simple model for the spread of epidemics. And this model was introduced in 1974 by Harris. And this is the simplest continuous time model that with a phase transition. And initially it was exclusively studied on ZD, the D-dimensional lattice. But later on in the 90s, people started to examine the contact process on homogeneous trees and then on more general graphs, and they realized that it exhibits interesting phenomena on more general graphs as well. This can also be seen as the continuous time equivalent of oriented percolation models. So a lot of tools, techniques, and results that we can use for oriented percolation automatically transfer for contact process. All right, so now for the contact process, I will assume that it takes place on a locally finite connected graph G. By locally finite, I mean that every vertex has a finite degree. So in every neighborhood, I can give a bound on the highest degree of the vertex in that neighborhood. And it's in a connected graph. And these graphs are usually infinite graphs, although there are some work that looks into how the contact process behaves on finite graphs. And so this is a continuous time Markov process, and the psi t will denote its state at time t. And the vertices can be either in state 0, which corresponds to that vertex being healthy, or state 1, which corresponds to the vertex being infected. And the contact process is characterized by its rate lambda, which is a non-negative number, and this rate determines the transitions of the vertices. Now the transition rules are as follows. For every vertex that is in state 1, that is the vertex is infected, it can recover, so become healthy again at rate 1. This means that after an exponential time with parameter 1, every vertex in state 1 flips to state 0. And this rate 1 is called the death or recovery rate. This can be a bit confusing, but by death rate, we mean the death of the infection. And when recovery, the recovery of the individual at that vertex. And if a vertex is in state 0, that means the vertex is healthy, then it can get infected from its already infected neighbors. And each infected neighbor will transmit the infection to this healthy site at rate lambda. So after an exponential time with parameter lambda, each infected neighbor transmits the infection to the healthy site. So the more infected neighbor you have, the more likely you will become infected. And this lambda is called the infection rate. Now the process starts from an initial configuration A, which is the set of initially infected vertices at time 0. And I will denote the process with initial configuration A by psi Ta. And I will often associate this psi Ta, the state of the process at time t, with the set of the vertices that are infected at time t. Now the process exhibits a well-known graphical construction, which is a space-time picture of the model. So we look at the graph G and we look at the evolution of G at a time, in time. Now for each X, for each site that we have in G, we assign a rate 1 Poisson point process to that site that I denote by dx. And this will correspond to these recovery marks on the picture, these x's. And for every edge, xy, which is an oriented edge, so this is an ordered set of vertices, xy. So for each of these ordered set of vertices, we assign a rate lambda Poisson point process, dxy, and this will correspond to these infection arrows. And once we have a representation, so we sampled these Poisson point processes, then we can define an infection path. And an infection path is a path that moves in the increasing time direction. It doesn't pass through any recovery marks, but it can pass through infection arrows. And having all these Poisson processes and defining the infection path, if we have an initial configuration of 0, 1s, looking at this graphical representation, we can tell what are the infected vertices at some time t, namely a vertex, like for example, this is infected at time t if there is an infection path that starts from a vertex that was infected at time 0. If there's an infection path that starts at that vertex and ends at this vertex here. This graphical representation is a very useful tool, and we can deduce interesting properties of the contact process from this representation. Here's an example. I hope it's visible. So this is an example of the graphical representation. These red things are the infection passes, And as you can see in the first picture, we have a very small infection parameter. So we have barely any infection pass and they stop very soon. And in the last picture, we have a very high infection parameter, so the infection can spread very fast. As you can see, a lot of almost all of the vertices are infected at every point in time. All right, now we can look at what properties this contact process has. First of all, the all healthy configuration is a trap for the dynamics. As we have seen the transition rules, you can only get infected if you have an infected neighbor. So once everyone recovers, the infection will not appear again. Now, if we look at the probability that the process starting at some initial configuration A ever reaches this all healthy configuration, then it is easy to see that if we increase the infection rate, so the infection spreads faster, then it will become harder to reach this all healthy state. Also, if we increase the set of initially infected vertices, then again, it will become harder to reach the all healthy state. And similarly, and finally, if we increase the graph, so we add edges and vertices to the graph, then the infection has more space to spread out. So again, we decrease the probability of ever reaching this all healthy state. Another property is that if we start the process from a finite initial configuration A, then for every other finite set B, there is a strictly positive probability that B will get infected, completely infected at some point in time. And this we can just see that we can define infection passes that start from A and make in every unit time jump to the next vertex on the path towards B, and these passes has a small but strictly positive probability. Now, as a result from these properties, we can conclude that for every finite set of initially infected vertices, the probability that we ever reach this all healthy configuration is either 1 or strictly smaller than 1. We have that this is true for all finite initial configuration, regardless of the configuration, because of this third property, namely that if we start from a finite set, then we can reach any other finite set, and then we are in the same position as if we started from that other finite set. So regardless of the initial configuration, we either die out for so we reach this all healthy configuration, which we say that the infection dies out, or there's a probability that's strictly smaller than 1 to reach this all healthy configuration. And in this case, we say that the infection survives. Now, whether survival or extinction happens depends on the underlying graph G and on the parameter lambda. And we can see that as we increase the parameter lambda, it's becoming harder and harder to die out. So the model exhibits a phase transition. We can define the critical parameter lambda C of the graph G as the supremum of the parameter values of lambda for which the infection almost surely dies out, starting from every finite initially infected set. Another important properties, another important thing that we can look at when we talk about interacting particle system is invariant measures, the distribution of the ones on the graph. But before we talk about invariant measures, I'd like to mention the property of self-duality, which will be important when we talk about the invariant measure. Self-duality means that if we start the process from an initial configuration A, then the probability that at time t, the infection will reach some vertices in the set B is exactly the same as if we started the process in a set B and then reaching some vertices at time t in the set A. And to see that, again, we can make use of the graphical representation because we can look at psi TA as the process starting from time 0, from some set A, and moving in the increasing time direction. and we can look at psi tb as a process starting at some time t, but moving in the decreasing time direction and moving backwards along arrows, so kind of reversing arrows. And then when we can reach from some site in A, something in B, that's exactly the same that's reaching from something in B, moving in the decreasing time direction down, reaching something in A. So this self-duality is a very nice property for the contact process, and this is very useful when we talk about invariant measures. So when we look at invariant measures, we can define a lower invariant measure and an upper invariant measure. A lower invariant measure is something that's below every other invariant measure, and an upper invariant measure is something that stochastically dominates every other invariant measure. Now, by monotonicity arguments, we can see that if we start the contact process from an initial configuration of all zeros, everything healthy, then we will converge to the lower invariant measure. Now, in this case, the lower invariant measure is just the point mass on zero, because then we just end up with healthy sites all the time. And if we start from the largest possible initial configuration, that is everyone's infected all once, then we will converge to the upper invariant measure, and I will denote this by mu bar. And so this stochastically dominates every other invariant measure. Now the question is whether this upper invariant measure is different from the lower invariant measure, because of course if we have small infection rates, then it is possible that even from all ones we will converge to the lower invariant measure, which is the point mass on zero. And so we want to see when does this happen, that mu bar is actually different from the lower invariant measure. And to do that, we can relate the upper invariant measure to the extinction probability using self-duality. So if we look at the probability that our process never dies out, then this is the same. So for all t, the process is not the all healthy configuration, then this is the same as we look at the limit as t goes to infinity, the probability that psi t is not the all healthy configuration. And now at this point we can use self-duality, because the probability that from site x we do not die out at infinity means that from site X, there is an infinite infection path. So we can reach a vertex at infinite time. And then when we look at the self-duality, then this is the same as if starting from all ones, we can reach X. So we start from all ones at infinite times, which is exactly the upper invariant measure, and we look at the probability that from any of the vertices there is an infection path that can reach X, and this is exactly the measure that the mass that the upper invariant measure puts on X. So this is the upper invariant measure of the configurations for which psi X equals 1, and we have seen that above the critical parameter, lambda c, this probability of never dying out is strictly positive. Therefore, the upper invariant measure in this case is not the point mass on zero. So again, this critical probability not only separates dying out and extinction, but it also separates the regions where you have one invariant measure, the point mass on zero, and multiple invariant measures. So in this critical rate, therefore, determines three phases: the subcritical phase in which we die out and the process is ergodic because it has one invariant measure, the supercritical phase in which we survive and the process is non-ergodic because we have multiple invariant measure, and the critical phase, which is lambda equals lambda c, and in this case, we don't really know how the contact process behaves. And in each phases, we can ask questions about the contact process. For example, in the subcritical phase, we can ask how fast the process will die out. In the supercritical case, we can ask how fast it will converge to its invariant measure. But most of the questions concerning the contact process are in connection with the critical phase, namely how does the process behaves at the critical phase? What is the value of the critical phase? And in most cases, we do not know the answer for these questions. For some models, we know a little. For example, if our graph is the d-dimensional lattice, then we know that the contact process dies out at the critical parameter in every dimension, and we have lower and upper bounds for the value of the critical parameter. And later, these lower bounds in the case of the integer line was improved a bit, but in most cases, we cannot say even this much about the critical phase. Now, the thing that I would like to talk about in the rest of my talk is how local modifications can affect the behavior of the contact process, of the critical contact process. Now, first of all, I will have to say what I mean by local modifications. These modifications can concern the structure of the graph, namely we can add or remove edges or vertices to the graph. This modification can also be regarding the parameters of the graph, namely we can change the infection or death rate at some set of the edges and the vertices and see how it affects the contact process. Now, this change of behavior can again be two types. These modifications can change the value of lambda c, or these modifications can change the behavior at lambda c. So for example, if it survived at some lambda c and then I make some modifications and then it will die out at lambda c. And it can also happen that both the value and behavior changes due to some modifications. Now, it's quite natural to expect that since we are looking at infinite graphs, it is natural to expect that adding finitely many edges to the graph will not affect the critical parameter. And there was a conjecture from 2001 by Pimentel and Stacy that said exactly this, that if we have G and G prime, and G prime is the same as G, with the exception that we add a single vertex to G, then the critical parameter of G and G prime will be the same. So adding a single vertex to the graph doesn't change the critical parameter. And of course, that can be generalized into adding finitely many vertices to the graph. And also in the other direction, we can say that if we remove vertices from the graph finitely many, then it doesn't affect the critical value. However, when we remove vertices, note that this connectedness assumption is very important. So we can only remove vertices and that will leave the graph connected. And we will see later on why this is important. And this conjecture is still open in full generality, but in 2005, it was proven for vertex transitive graphs. And I will show now quickly the proof of this conjecture for the d-dimensional lattice because it's quite nice and simple. So in this case, our graph is the d-dimensional lattice and G prime is just the same d-dimensional lattice with an additional edge. And assume that just by adding this edge, we will change the critical parameters. So lambda CG is greater than lambda CG prime. Then we can pick a lambda value such that at lambda, the contact process on G prime survives, but the contact process on G doesn't survive. Now, since we are in the supercritical case for G prime, we know that there's a non-trivial upper invariant measure, U bar G prime at lambda. Now, if we look at U bar G prime of the configurations for which psi x equals 1, we have seen by the duality relation that this is exactly the probability of survival of the process from starting from a single vertex at x. Now we know that for G prime, we are in the supercritical region, but in G, we are in the subcritical region. So in order for this process to survive, it necessarily has to use this one additional vertex UV, because if it never used that vertex, then this would be just the process on our original graph G. And on that graph, we know that the process dies out. So when we have survival, we necessarily need U and V to be infected at some point in the process. So this is the same as the probability of survival and having U and V reached by the process. Now, there was an article by Bezout and Hot and Grimet that gave a bound on the probability that U and V, that from some X we will reach certain vertices on the graph. And I will not go into how it works, but they gave this upper bound e to the minus c times x, where this is the norm of x, and c is some constant. Now, because of that, if we sum this mu bar over all the sites in ZD, then this is gonna be finite, which means that mu bar of G prime, this upper invariant measure, concentrates on configurations with finitely many ones, but this contradicts its invariance. Therefore, our initial assumption was wrong, and lambda CG has to be equal to lambda CG prime. So this is the proof of the conjecture for ZD. In general, for vertex transitive graphs, the proof is a bit more involved. Now, in our case, instead of trying to prove the conjecture in full generality, we had a different line of thought. We made a construction of a graph that looks like this. So we have two graphs, G1 and G2. And we know that the contact process dies out for some values of lambda on both of these graphs. However, if we connect these two graphs with a single edge, E star, then we end up with one connected graph. And the contact process will survive for that parameter lambda on this now connected graph G. And note that this doesn't contradict the conjecture, because it was a very important thing, as I mentioned in the conjecture, that both G and G prime are connected. And in this case, when we remove E star, then we end up with two graphs that are not connected. So it doesn't contradict the conjecture, it just shows that indeed the connectedness assumption in the conjecture is necessary. And in fact, what we show is a bit stronger than this. So we show a construction of a tree, G, which has a privileged edge. And in this tree, G, the contact process survives for any parameter lambda. So the critical parameter is actually 0. And when we delete this edge E star, then we end up with two subtrees, G1 and G2. And for these subtrees, the contact process dies out for small parameters of lambda. So we show that the critical value of both G1 and G2 is at least 1/4. And now in the rest of the talk, I will show you how this construction is done. Now, one very useful tool when we look at the dynamics of the contact process are star graphs. Star graphs are trees. A star graph on n vertices is a tree with n-1 leaves. So there's a hub and it has n-1 neighbors. Now, if we look at the star graph, it is intuitively clear that the infection will survive on a star graph for a longer period of time, because if we start with a single infection at the hub, since it has a lot of neighbors, it will, with high probability, transmit the infection to a bunch of its neighbors before recovering. And once it recovers, it will have a lot of infected neighbors, and at least one of them will likely to transmit the infection back before recovering. So these star graphs maintain the infection for a longer period of time. And if we denote this time by tau, this random time, then it is known that this tau is exponential in the number of vertices of the star graph. And we have exponential lower and upper bounds. And these bounds were established in an article by Mountford, Vallesin, and Yao. So for small values of lambda, we know that star graphs maintain the infection for an exponential time. Now, how can we use this thing? When we look at a graph, then these star graphs corresponds to having vertices with high degrees on that graph. And we can use this to make sure that the infection around these vertices with high degree will be maintained for a longer period of time in that graph. And in fact, it will be maintained long enough to produce an infection path that reaches another vertex at a certain distance. So while the infection is maintained at the graph, each time an infection path starts. And this infection path reaches a certain distance, then it dies. Then another infection path starts, and since this goes on for a long time, we can give an estimate on how far the infection path can reach from that star graph in our graph. And this is exactly what we will use in our construction. So in the construction, we start from the integer line. And we will say that choose the privileged edge. And this will be the edge between 0 and 1. And so remember, what I want is that if the privileged edge is present, then the contact process survives. But if I remove this edge, then the contact process will die out. And I will give the construction recursively. So the way I do this is that I will add some star graphs to certain points of this integer line with increasing size. And the hub of the star graphs will be denoted by OI. So the first star graph I will position at -1, and I will add a single leaf to it. And I will determine the position of the second star graph as O2. So this is the starting point, and now a recursive step looks like the following. So first, I will determine the position of the next star graph, O3. And I will determine the position in the following way. The distance between O1, the first star graph, and O3, the third star graph, will be so big that an infection at O1 is not maintained long enough to reach O3. Once we have this, then we determine the degree of O2, determine how many leaves we want to add. We know the distance of O2 and O3, and we will add so many leaves that the infection will be maintained long enough around O2 to reach O3. So this is one step of the recursion. Now I will do this on the other half line. So first, I will determine the position of O4. And I will determine the distance between O2 and O4 in a way that an infection around O2 is not maintained long enough in order to reach O4. Then I will add leaves to O3. Again, I know already the distance between O3 and O4, so I know how many leaves I should add to O3 in order to reach, for an infection at O3 to reach O4 with high probability. And so on and so forth. Now I go again on the negative half line. First, determine the position of O5 such that an infection from O3 cannot reach O5. Then the degree of O4 such that an infection from O4 with high probability reach O5. So in the end, I will end up with this integer line with add infinitely many star graphs added to this integer line with increasing degree as we go further away from the origin. And this is the exact way the position and the degree is determined for the star graphs. And note that when I say that the degree of the star graphs increases as we go further away from the origin, it increases quite rapidly. In fact, it increases faster than I factorial. And indeed, when we have E star, this privileged edge is present, then from every star graph, the next star graph will be reached with high probability, and the probability of the intersection of these events is close to 1, therefore we have survival. And note that in this case, every infinite infection path will necessarily traverse through this privileged edge infinitely many times. But if this edge is not present, E star, then it will become increasingly difficult to travel from each star to the next star. So eventually this will not happen and the infection will die out. So this was our construction. So it's an example when you delete one edge from the graph falls into two pieces, and then the infection, and then the value of the critical parameter will change. And just to wrap things up, I would like to mention some related works. These works also look at how introducing local modifications can affect the value or the behavior at the critical parameter. There was a paper in '94 by Madras, Kinasi, and Schulman, where they examined the contact process on the integer line, and in this case, the infection rate was the same at every edge, but on some set of the vertices, they changed the death rate from 1 to some b, which is strictly less than 1. And they did this on infinite sets of vertices. So this set S is an infinite set, but they showed that if this set is sufficiently sparse, then this change will not affect the value of the critical parameter. So they introduced some changes on an infinite set, and yet it was possible that the critical parameter still didn't change. Another work on the contact process on the integer line by Newman and Washon in 1996. Again, the infection parameter was the same everywhere, but the death rates now followed some, were random, and they followed some distribution, and they established some conditions for the death rate distribution under which the contact process will survive for any value of lambda. So in that case, the critical parameter is 0. And in 2003, Handiani, he was looking at the water model, so not the contact process, but this water model, which was a model for competing opinions. And he showed that in that model, in fact, changing the flip mechanism in a single site can actually change the behavior at lambda c. So it had probability 0 at lambda c of survival, and then changing the mechanism at a single site changed this probability of survival to positive. Yeah, so I would like to thank you for your attention.
Thank you very much. Any questions and comments? Please feel free to unmute yourself and ask your question or comment.
Okay, maybe I can ask a little question. Hi, Réka, nice to see you here also. So these agent-based models are they corresponds to differential equations? Did you check that?
Yes, you can define differential equation and also to this time evolution of the model. I look at these models from a different point of view, but yes, you can define the corresponding differential equations.
But I mean, is this improve our understanding? Yeah, I mean, yeah, of course, it improves our understanding from differential equation point of view. I'm just trying to compare these two things and understand what you did. So it was great.
Thank you.
Maybe we can wait a few seconds if somebody, for people to feel comfortable to ask a question or something. Okay, I guess not. Thank you very much again for your talk. We will have 2 hours break now, and after 2 hours, we will continue with the afternoon session, and Ceyda Şimşek will be talking on non-relativistic gravity. See you soon.
Thank you, Réka, again. Have a nice day.